Okay, it's 11 o'clock. Good morning, and welcome to yet another online session of Chai and Why. So, on the first of the month, we should have been at Prithvi Theatre. Unfortunately, we still aren't there at that beautiful venue. So, you'll have to bear with us on YouTube and Facebook Live. And if you're watching us live, this is a good chance for you to make sure that you can hear and see what's happening. And remember that please do post your comments, questions, etc. on the type them in on the chat of the YouTube channel or on the comments in the Facebook page. Okay, one good thing that's of course happening before I start this session is that Chai and Why has traditionally happened every other week. But in November, since we are anyway online, we're going to have a Chai and Why on every Sunday of November. Every Sunday of November, starting now, we're going to have a Chai and Why. November happens to be one of the months with 5 Sundays. So there are going to be 5 sessions this month. Today, of course, it's going to be about the moon. But after this, November is the Nobel Prizes month at Chai and Why. And we're going to bring you 4 talks by our students. And if we really want to make it simple, I think there's no better way than to ask our own students to be talking about it. So we're going to have a series of 4 talks. There's going to be start off with physiology and medicine, the prize for the hepatitis C virus. Diksha will cover that. Followed by that, Sharanya is going to talk about the Penrose part of the physics prize, where he will take us from how general theory of relativity was connected to black holes. We will take a break and move to chemistry and discuss CRISPR. Tuli and Mahima, they will do a Jugalbandi to honor the 2 ladies who won the CRISPR prize. And we will end with, again, the physics prize going back to the black hole at the center of the Milky Way, which Lankeshwar plans to talk about. So do join us on all the Sundays of November with Chai and Why sessions on the Nobel Prizes. Okay. With that, it's time to introduce our speaker for the day. Jatan, can you turn on your video? We can't see you. Yes, there is Jatan. And this is a talk, a session which should have happened actually a long time ago. And we sort of had planned it, but it had to get canned because of COVID. And we decided that better late than never, let's do it. Jatan used to be our science writer and social media person at TIFR till COVID intervened. But we thought, hey, the moon is back in the news. People keep finding water on the moon every so often. And this is a great time. Jatan is a person who is literally moonstruck. I mean, he is everything about, it's his favorite body apart from Earth, I guess, in the solar system. And yes, his t-shirt says that as well. So Jatan's, of course, had a history with, he was earlier with the Indus mission that was aiming to put a rover on the moon. And he's going to tell us more about essentially water on the moon today. But I hope you guys have all at home got yourselves a glass of water to drink and are all ready with this session. And remember, if you cannot hear us, cannot see us, if anything's there, please do type in your comments, because that's the only way we'll get to you. So over to you, Jatan, and all yours. I will mute myself.
All right. Thank you, Arnab, for that introduction. And thank you for having me here. So hello, everyone. I am Jatan, and let me just quickly share my slides here. Okay, I think. Just a sec. Okay. So I have my slides, and let us begin. So just quickly to start with an introduction of myself. So I'm those who don't know about me, I'm a science writer, and I'm passionate about space exploration, everything space exploration essentially. And my articles have been published on the Planetary Society, the Wire, and other such global publications. And I also self-publish on my own website, that is at jatan.space. And before doing science writing as a profession full time, before taking that on sometime last year, I was at TeamIndus. And at TeamIndus, my job was essentially to select where on the moon should we land. So TeamIndus was building a lunar landing mission, very similar to Chandrayaan 2, in fact. And the idea was that the engineers would build the mission, and I would be selecting, since I have a science background, my background is in physics, I would be selecting where on the moon should we land, because the moon is geologically diverse, just like the Earth. So on the Earth, you have Himalayas, you have Sahara, and those are not not the same kind of places, you know. So the moon is also like that. It has many diverse places, and so if you go to one place over the other, there are better scientific benefits. So the idea was to do that, and after Team Indus, I was at TIFR as the science writer and social media person, and I do public speaking, as you can see now. So, okay, let's just get started with the talk. Um, so, we, as everyone knows, we have landed on the moon 50 years ago, and I hope everyone knows that. So, we landed on the moon over 50 years ago, and we did it not once but 6 times. We landed humans 6 times, that is. Robotic missions have been far more than that, of course. So, between 1969 and 1972, we landed six human landing missions on the moon, and that involved 12 astronauts walking on the surface of the moon. And that's a technological feat that I am still yet to get over, no matter how many times I think about it. And so, yeah, that was that. And here on the right, you see the footprint of Buzz Aldrin. He's, by the way, on Twitter as the real Buzz Aldrin. Uh, he's that famous. So he's on Twitter. You should check him out. And so yeah, so we landed on the moon 50 years ago, and we after that we sort of had a downward trajectory. You know, so the thing about technology is that it doesn't advance just because time passes by. Someone actually needs to put in the effort to, you know, keep it advancing. So for example, why did we stop going to the moon when we had already done it 50 years ago? So at the time it was political, and that cannot be forgotten. So since the Soviet Union could not land humans on the moon at that time, there was no incentive for the US to go back and extend the frontier to Mars and beyond, in fact. So, a lot of the plans that were actually being made for not just living on the moon, but also sending humans to Mars and so on, were simply cancelled because there was no political incentive. So, after that, we have been doing sort of small things here and there. Those things within themselves are very complicated, just to be clear. But of course, it's no such thing as a feat on, you know, as landing on the moon. So the ISS, the International Space Station, it's basically a floating laboratory 400 kilometers above the moon's surface. Sorry, above the Earth's surface. And it's just 400 kilometers above Earth. It's not that far actually. And it's well within the thin atmosphere of Earth. So it's not technically, you know, in space. It does feel the drag of air, however slightly, however small. It does feel that drag, and it needs to keep correcting to compensate for that. So basically, we have had the International Space Station online for in orbit for 22 years, and of that 22 years, 20 years for 20 years, it has seen human presence constantly. So there, since 2000, there has never been a single person, a single time in our history when we had all of the humans living on the planet. There has always been at least one person on the space station. So I think that's something to think about, and that's an incredible feat to have kept this space station going. And just to be clear, the space station is a multinational effort. uh, uh, Major contributions come from the US and Russia, and then there are many contributions also come from Europe as a whole, and Japan and Canada and so on. India, by the way, is not part of the International Space Station, and they are not planning to be either. I don't know why. I think they should, but anyway, I think the talk on ISRO can be a separate talk. So yeah, okay. So now context, we landed on the moon 50 years ago. We have had humans staying in space for as long as a year at time, in fact, even for 20 years now. So the next question is, you know, why aren't we living on the moon already? It does seem like we have the technology. So what is missing? And we have the money, by the way, and it's not a money problem per se, strictly speaking. I mean, have you looked at the military budgets? It's just skyrocketing, no pun intended. So, so the question is, why aren't we living on the moon already? And the first thing that pops to mind is rockets, because if you ask this question to an engineer, the first thing he would say or she would say is, we already had the Saturn V, which is the rocket responsible for sending humans to the moon. It was a gigantic rocket, and yeah, you can see that here the Statue of Liberty and the Saturn V is being compared. And the first thing is opinion time. I think we should just replace the Statue of Liberty with the Saturn V. It's just marvelous. Anyway, so the Saturn V is huge, okay, and it could put about sorry, it could put about 1,40,000 kilos in Earth orbit, and about 30-40,000 kilograms on the moon. So that is when you can, put 3 humans inside a capsule with the life support system and send them to the moon. So you need to have the ability to send about 30,000 ish kilos to the moon with a rocket, to be able to sustain a human presence. Now, what is the best rocket that we have right now in this day which is working? The Saturn V, of course, is abandoned. It's no longer operational. So let me just have some water. So here's the Falcon Heavy, which is the most powerful rocket that we have right now, and it can put about 63,000 kilograms to Earth orbit. And that's a lot, but it's just not enough compared to the Saturn V. And if you take the moon, if you send something to the moon using the Falcon Heavy, then it can do only 8,000 kilograms, which is far shy of what you would need to send at least 2-3 humans to the moon. So we don't have uh, rockets powerful enough to be able to send flights to the moon and at a good frequency. But of course, I know some of you know that uh, SpaceX is building the Starship super heavy rocket, which is going to be even more bigger than the Saturn V. And of course, NASA is also building their own Saturn V successor, which is going to have similar capacity as the Saturn V. It's going to be called the Space Launch System, or SLS. And that will come in time. It's been getting delayed forever now, and it's almost become a meme in the space industry. People, I mean, I have friends who are sharing memes with me about the SLS becoming getting delayed again and again and again and again. It just never gets old. So I think there's still quite a while before we can have that kind of rockets again, uh, as powerful as the Saturn V. But even then, it's still not more than 5 years away. Let's say, okay, it's not more than 5 years away, and that's a realistic estimate. That's not a political deadline. So then what is the problem? I mean, it's just a matter of engineering, right? No, so there are more technical issues. So let's start so this is the context, and now I will focus on the major issue, which is at the root of not being able to live on the moon already. So let's start by looking at where the past space missions have landed. Okay, so here I'm showing all the landing sites for past missions, and this includes both human landing missions, that is the Apollo ones in yellow, and the robotic landing missions by everyone else. So you can see Surveyor, which were American robotic landing missions before Apollo, which is what gave America the confidence to send humans. So Surveyor missions are here in blue. And then you have the Luna missions, which are among my favorite missions by the Soviet Union, and they were really cool. It's just that Apollo happened, and so they sort of lost the limelight. But Luna missions by themselves were really cool, and they did stuff in the 1960s, robotically, autonomously, which was not even conceivable at the time. And then there's the Chang'e 3 in orange, uh, by China. So China landed a robotic lander on the moon in 2013, and Chang'e 4 also and Chang'e 4, which is its successor, is another robotic lander which they landed on the moon's far side, so which is behind this, and so I cannot show it here. But that was also a robotic lander, but it was the first lander to ever land on the far side. and to this day remains the only one. So with that, here's the map of where everyone landed. Now, what I want you to note here is something very peculiar. Uh, so just look at where each of these dots are. So let's just take random ones. Okay, I'll take the Luna 2 one. Okay, it's in the dark region of the moon. Okay, it's this dark patch. Luna 21, again near a dark patch. Apollo 11, near a dark patch. Luna 9, dark patch. Chang'e 3, dark patch. The early exception seems to be Surveyor 7, which is on the bright area, and the Apollo 16, which is on the bright area. Everyone else is either very well in the dark patch or very near to the bright area, but still in the dark patch if you zoom enough. Okay, so now what's the deal here, right? This is the engineer thinking. Okay, so here's a quick view of what those patches mean on the moon. So whenever you look up to the moon, and this is a great time, it's the full moon now almost today. So tonight you can go and look up to the moon and think about these things, I hope. So these dark patches are essentially solidified lava flows. So the moon used to be volcanically active at a point in time, at various points in time, 1 billion years ago, 3 billion years ago, and so on. And so these dark patches are actually lava that solidified over time and now is sort of like a desert. Okay, so so this is sort of like a leveled desert more or less with only few ups and downs. So these are dark solidified lava flows, and the bright areas are rocky mountainous type areas. So obviously you go to an engineer, you tell him, we need to land on the moon. It's already a difficult task, obviously. So the engineer will engineer will say, it's already a difficult task. Why should I make it any more difficult than it should be? I'll just land on the area which is smooth and flat and nice. And so, which is why you got all of these missions landing in the dark patches of the moon. Okay, so that's one thing to keep in mind. I will relate to this to the problem just in a moment. Okay, so I hope everyone is with me till here. If you have questions, just let TIFR outreach know in the chat, and we can clarify that. So I'll move ahead. Okay, so you must have noticed one site that was missing in this last slide was the Chandrayaan 2. Of course, Chandrayaan 2 lander unfortunately crashed and did not make it in one piece on the moon. But the landing site, which ISRO, sort of touted as being a polar landing mission, world's first polar landing mission. Um, so Chandrayaan 2 was supposed to be like this, and the landing site of it was this. It's almost towards the pole. Okay, but again, if you notice, again, this is sort of like a nice solidified lava plain area which they chose, and it is fair. I mean, it's what any sane person would do. So this is what the landing site was, and so that's almost near the poles. All right. So, and ISRO sort of made a big deal out of it that it's a polar mission and the world's first polar landing mission and so on. And I want to be clear. I just want to clarify that it's not technically a polar mission. It's 71 south, and the polar circle equivalent for the moon starts beyond 80 degrees south. But there is a physical reason also beyond, just semantics. So I'll come to that. So, okay, so here are composite pictures of the North Pole on the left and the South Pole on the right of the moon. Okay, so this is not how it would look like in real life, because only half of the moon would be lit, whichever half is facing the sun. But this is a composite picture put together from many pictures, so as to give us an idea of what it looks like. Now, so this is, as you can see, the polar regions are anything but nice and flat and smooth and like the dark patches. They are heavily cratered, and crater means danger essentially for the engineer. uh, and it's essentially an engineer's nightmare to land on a crater and drive inside a crater and so on. And they are also mountainous. So it's like the worst of both worlds. So you take these rocky areas and the craters, you combine them both, and you get this. So the polar regions, the true polar regions, are very rocky and they are heavily cratered. Okay, so that's one of the biggest reasons why people haven't really tried landing on the polar regions, true polar regions of the moon. Okay, but that's just skimming the surface of it. It gets worse. Now, the second part is, uh, this diagram looks complicated, but I don't want you to read any of this stuff. I just want you to focus on uh, the moon here and ignore the earth, and just put the sun instead of the earth. Okay, so the only thing that you need to know out of this diagram is that the moon is, if this is the sun and the sun rays are coming in like this, the moon is not tilted with respect to the sun. The earth is tilted by 23 degrees, and we all know that. But the moon isn't. The moon is tilted by just 1.5 degrees. So that's practically negligible. 1.5 degrees is not a lot. So for all intents and purposes, you can assume it to be perpendicular to the plane. So so yeah, so this is the geometry I need you to just keep in mind. This is the sun. Sun rays are coming in like this. This is the moon. This is the north pole of the moon. This is the south pole of the moon. All right. So now imagine you are on the north or the south pole of the moon, any of the poles, pick anyone you like. And you're standing on the surface of the moon, on the polar regions of the moon. So for you, the sun, which is represented here by these colored lines, would essentially take any of these paths. So the sun, because there is no difference, there is no tilt of the moon towards the sun. The sunlight is, if you are on the moon and if you are looking at the sun, then the sunlight is very close to the horizon. So it's like watching a sunset, which just doesn't end like at all. So imagine a very, a close to the sun, a sun close to the horizon, which just doesn't seem to set. Or even if it sets, it sort of comes back, but only keeps on hovering near the horizon. So essentially, what you would see is the sun doing a 360-degree path around wherever you are standing over the entire lunar year. A lunar year is essentially, one full, uh, a lunar day is essentially a one full rotation of the moon, and a year for the moon is one full revolution around the earth. So in this case, we are considering the sun. So if you stand on the surface of the moon on the poles for one day, then you would see the sun very close to the horizon, going 360 degrees. All right. So the essential thing here is the sun is very close to the horizon, and that's about it. It never goes high up in the sky. There is no such thing as, heated afternoon or anything like that. So that's the one problem. Now the second problem is, notice this black lines, which is sort of a representation of the terrain that you would find on the poles. So as we said, the polar regions are very rocky and they are heavily cratered, which means that, so if there is a rock, even a single relatively small rock the size of a tree, let's say, in front of you, and the sun is behind that, because the sun is not going more than 1.5 degrees, 2 degrees on the sky. So since the sun is very close to the horizon and there's a rock in between you and the sun, the rock will block the light of the sun. And not just that, since the sun is very low, the shadows will be really long, right? So you will have like really, really long shadows. So any and all rocks on the moon will essentially start blocking out sunlight for a for the entire area behind it for a really long distance, right? So because the sun is not going high up in the sky at all. So the takeaway here is that, apart from being rocky and terrible for engineers, the sunlight on on the polar regions of the moon is very bad. The presence of sunlight, it's just shadowed most of the time and most of the areas, and very few areas which are higher up, like the mountain top, or if you stand on a rock for some reason, or things like that. So only those areas are receiving good sunlight. Everyone else is sort of deprived of sunlight. So, and which is why, this I have this subtitle: a small obstacle can literally ruin your day. And so now let's take a real image. So this is an image taken by NASA's orbiter. The orbiter is called Lunar Reconnaissance Orbiter. It is orbiting the moon right now as we speak. It has been doing so since the last 11 years now. And this is the image that it clicked of the crater on the moon. on one of the poles of the moon. So what you can see here is, since the so if you imagine a crater, right? So let's say this is a flat surface. Okay, I hope I'm in the frame. So this is a flat surface, and there's a asteroid coming in and hitting the surface and creating a crater. So what happens is, because the asteroid is depositing, you know, a lots of energy onto the surface sort of bounces back, right? So you have an asteroid impacting the surface, creating a crater, and the surrounding areas sort of get uplifted, right? Because of the bouncing back effect, right? So whenever you have a crater, you have uh, this sort of a geometry. So you have flat surface, elevated rims of the crater, and then the crater itself. So sort of like a terrace, right? So when you go on the terrace, you have terraced rims, and so it's sort of like that, right? So basically, you can see here, and this is a real image, that there is absolutely no light on inside the crater, and the only thing you can see pretty much is the rim of the crater, and even then there are many areas there which are deprived of sunlight, right? So basically you have uh, just a sec. Yeah, yeah. So basically you have absolutely no light inside the craters, and these are really large craters, by the way. So I'll just give you a sense of scale here. And so the moon is about 3,000 kilometers in diameter from end to end, right? So, and you can see some of these massive craters on this very scale here, right? So in fact, when you go and look up to the moon, you can see craters with your eyes. So these craters are hundreds of kilometers wide in some cases. Like, just look at this thing. It's like about 500 kilometers or so. And here, and even this thing is like 100 kilometers or so in diameter. So these are huge craters, right? So imagine, craters the size of three cities, or the size of Mumbai, like proper extended Mumbai in this case, uh, completely deprived of sunlight. And the only sunlight that is coming to you is on the edges of the craters, which is the rims, right? So these regions are called such. There are many such areas. So if you come back to the map here, you will see. Now again, this is a composite image. This is not a real image. In reality, many of these craters would not have light, uh, or at least not as much of it. So there are many such areas where, if the rim of the crater is high enough that it blocks the sunlight, which means if it is higher than 2 degrees from the surface, then it will block the sunlight. So those craters will never get light. So there are many such hundreds and hundreds of craters which are simply not getting light throughout the year for 4 billion years, right? Just 4 billion years, no light. And such regions are called permanently shadowed regions. I mean, just a basic name. And remember, these are physicists and geologists studying the moon. So these are the naming scheme sort of should be very literal, unlike biology. But yeah, anyway, so these regions are called permanently shadowed regions. And I want you to take note of this, because I will be using this acronym PSR in these slides going forward. So I hope everyone is with me here. And if you have any doubts whatsoever about this concept, then just ping on the chats and let me know. I will clarify that and we'll move ahead. Okay. So all right. So now coming to the crux of the issue. Chandrayaan 1 finds water ice on the moon. This was the headline uh, about 11 years ago, and it made headlines in every part of the world, not just India. And it was a big deal. I mean, there's no question about that. It was a very big deal. But so, where is this water? As you must have already guessed, it is inside these very dark regions, the permanently shadowed regions on the moon, inside these PSRs. Now, why isn't it outside these permanently shadowed regions? The answer is very simple. If you take the moon's surface, typically not the polar regions. If you take the regular moon, right, the moon's surface experiences temperatures ranging from about as high as 120 degrees Celsius uh, during the day to minus 180 degrees minus 180 degrees, mind you, almost close to liquid nitrogen temperatures. Uh, so minus 180 degrees to on the night side. So it ranges from 120 degrees hot to minus 180 degrees cold and everything in between. And the more important thing here is the moon doesn't have an atmosphere. So since there's no atmosphere, because the moon doesn't have enough gravity to hold on to a substantial atmosphere, the atmosphere that the moon does have is like very thin. It can barely be called one. It's an exosphere, to be technical. So it's like very few atoms, just suspended above the moon's surface. It's not essentially atoms. For those who are technically inclined to understand the difference between the atmosphere and the exosphere, the main difference is in an atmosphere, the atoms and molecules interact with each other at a substantial rate. And in an exosphere, the atoms do not interact with each other. They are sort of more like suspended, and they rarely, come in contact. So the moon has an exosphere, to be very specific, and it's very thin. It's barely anything. And so what happens is you can treat it almost as if it's vacuum, right? So what happens is, let's say if you drop a mug of water on the moon, and if you are, let's say, somewhere here, right? Let's say you're an astronaut, you're on Apollo 11, and you go and just drop a water, drop of a bottle of water on the moon. And that would be a very bad thing to do, by the way. Just to give you a context, one bottle of water on the moon will cost you $1 million, and I'm not kidding about that. That's the uh, cost estimate for sending a bottle of water on the moon. Uh, so it's about $1 million. So that's a stupid thing to do, but let's say you do it anyway. You drop water on the moon, and what would happen essentially is, if you're on the day side, it would not almost instantaneously evaporate. Some of it would make it to the ground and be absorbed by the ground, but even the ground is very hot. So it's again, it's at hundreds of degrees, a few 100, 110 or so on. It's very hot, so some of it would get absorbed, some of it would evaporate, and so on. If you do it on the night side, then obviously it would freeze. But as soon as the moon rotates and the night side becomes the day side, the region where the night was enters the day, then the water would evaporate again. And since the moon doesn't have enough gravity, most of that water would escape to space, because it's directly exposed to space. There's no atmosphere, there's no shielding whatsoever from any atoms. So the water would escape eventually to space in a matter of some time. So basically, the moon does not have the ability to retain any substantial amounts of water at all on its surface. The only exception are the polar regions, because you have this area where you are exposed to vacuum, yes, but you're not exposed to sunlight. So since there is no sunlight, and since the temperature is very cold, and again, since there is no sunlight, there is nothing delivering energy to your water to be able to escape the moon, right? So essentially, if let's say somehow you put water inside these hundreds of permanently shadowed regions on the moon, then the water would just stay there, because there's nothing heating it up. There's no evaporation happening and nothing else. So it's essentially going to be frozen in the form of water ice. Now, this is exactly what Chandrayaan 1 discovered. So Chandrayaan 1 discovered water ice on nearly all of these permanently shadowed regions. So this is again not a real image, a composite one. This is a radar image actually, which is slightly tweaked for public viewing. So this is the South Pole here, and this is the North Pole, and these blue areas are where the water is represented. So this is the water ice, and you can see the South Pole has substantially more water ice than the North Pole, at least from the observations of Chandrayaan 1. And how did Chandrayaan 1 have these? Find these? Basically, it used radar. So this is a sort of a artistic picture of the Chandrayaan 1 orbiter using a radar, bouncing radar off of the moon. And then based on how the radar is reflected, the material which is present on the surface will reflect the radar based on its properties. So water has a distinct water ice has a distinct signature, and we know that from labs, for example. So if you get that same signature, then you know that it's water ice. So basically, Chandrayaan 1 found lots of water ice on the south pole and the north pole of the moon inside the permanently shadowed regions. Okay. Now the next question is, where did this water come from in the first place, right? Like, the Earth has lots of water. In fact, where did Earth's water come from? If if you go back to the time 4.5 billion years ago to 4 billion years ago, when the solar system had just formed and the planets had were newly forming and taking, taking shape from a molten ball sphere to some and solidifying over time, the Earth and Mars and Venus and Mercury, all of the inner planets, were too close to the sun, and things were too hot to, have to retain any water, because we know, on atmospheric temperatures and pressures, in atmospheric pressures, water boils away at 100 degrees Celsius. So if you are saying that the earth has formed in a very hot state, then it is logical to presume that most of that water must have been lost anyway. So what is this, so much water in the oceans, and where is this coming from? And that's the same answer as where the moon's water is coming from. It is asteroids and comets and micrometeorites. So 4 billion years ago, there was a period in the solar system uh, in which many asteroids and comets were just running rampant, free floating in the solar system. It's almost as if someone gave them a free pass to shoot bullets across the entire solar system. And so you had these large asteroids and comets just, going haywire across the solar system, impacting moons, planets, and everything that they could impact that was in their way, essentially. And these asteroids and comets have water. We know that they have water from our current observations of spacecraft and current radar observations from radio telescopes on Earth as well. So we know they have substantial amounts of water, and that water, that is the water that they must have delivered, as in, of course, not the same asteroid, but the ones that impacted earlier. So after the Earth formed and solidified and sort of cooled down a bit, and after its young intense birth era, we these asteroids and comets, which were constantly bombarding, brought the water to Earth. Some of it again evaporated and escaped, but a lot of it stayed. So the same mechanism is true for the moon, except, since, as we discussed, the moon would, any water on the uh, you know non-polar regions of the moon would escape and evaporate eventually. But if the water ended up in the uh, uh, permanently dark regions, and it is a substantial volume of the moon, it's not small by any means. So if you just, do a simple calculation, then you would see that there is going to be enough water that's going to be deposited inside these permanently shadowed regions, and they just stayed there over time. So the idea is, the water ice inside these permanently shadowed regions on the moon, after being deposited 4 billion years ago, and then at some points in time after that, when, occasionally asteroids and comets keep striking, because we cannot forget the dinosaurs, that was just 65 million years ago. So occasionally more bodies keep on striking and keep on depositing some water or the other. But essentially, this water ice has not seen sunlight in 4 billion years. It's that pristine, and it has that the pristine nature of it means that it has scientific benefits. And because for a scientist, this water ice is representative of what happened in the solar system 4 billion years ago, and not just with the earth and the moon, but the entire solar system. So it's sort of like an ancient archive, a museum, if you will, right? So that's the scientific value of that. And so what happens is, so that's why scientists are interested in this sort of areas, and that's why they were partially looking for it. But of course, the question of our talk is, you know, why can't we use this water for building the habitats for living on the moon? So now, so this is what Chandrayaan 1 found. I hope everyone is with me again till now. If you have any doubts, please let me know and we'll clarify that. So going to the next slide. So this was Chandrayaan 1 was in 2009. Okay, in the same year, uh, the NASA orbiter which I mentioned, which took this image. This is the artist impression of the lunar reconnaissance orbiter. It's I mean, it doesn't look that great in this artist impression, to be honest, but it's a nice orbiter. It's in fact my favorite orbiter ever. Okay, so this orbiter had an extended spacecraft extension, which you can see in this impression. Oops, sorry, just a sec. Yeah, so the this extended spacecraft, this spacecraft was attached to this orbiter at launch, after which it separated. And you can see that it had another extended spacecraft, as you can see, as this projectile thing going away from this spacecraft. So this was basically the upper stage of the rocket. So this orbiter launched on a rocket by ULA. ULA is a company which, by the way, not many people know about. Most people just know about SpaceX, but I would encourage you to look up ULA by googling them later on. Uh, but in a sense, ULA has been the company responsible for most of NASA's missions. So all of NASA's uh, Mars missions, for instance, all of them launched by ULA. And I had the good honor of interviewing uh, ULA's CEO, Tori Bruno, just some time ago when the Mars 2020 launch was happening in May. So that interview is on my website, so you can go check that out. So anyway, coming back. So basically, these two things where my pointer is, those were the upper stage of the rocket connected to this satellite. Okay, and what happened is, after they reached the moon, this stage separated, and a part of it was intentionally made to crash on the moon. So not all crashes on the moon are, unintentional or an accident. So this probe was made to crash on the moon, and not just any part of the moon, in one of these craters on the moon. So they wanted to see and verify ki, you know the water ice which we have found from Chandrayaan 1, is it really there? I mean, they were very sure, but nevertheless, this would be like super confirm evidence. And but the more important thing is, they also wanted to know how much of it is there, right? So they just shot this entire thing into a dark crater on the moon. And if you can see here on the screen, this hazy thing, right? This hazy little thing, if you can see, and the scale here is 10 kilometers. So it's about a 7-ish kilometer wide plume. So after the spacecraft impacted on the surface, you had a 7 kilometer wide plume of vapor coming out of the water, coming out from the surface. And this spacecraft, the second spacecraft, had instruments which could detect what chemicals are present inside this vapor. And what do you know? You find water. It was a clear sign of water inside a permanently shadowed region on the moon. And they estimated the water to be about 155 kgs. So that was nice, I think. And this is sort of the games that scientists like to play sometime on a cosmic scale. They sort of like to play God sometimes. So yeah, so I think these two missions essentially solidified the idea of water being present on the moon. Now, just to clarify here, um, Chandrayaan 1 is not the first time that scientists had a hint that there is water on the moon. The theory that asteroids came, impacted the moon, and left water, and they must be in the permanently shadowed regions, the theory had been there for a while, for many years, in fact. And it's in 2009 that Chandrayaan 1 finally confirmed it. But missions before Chandrayaan 1, and there were many missions before that, had already seen hints, indirect hints of water ice being present using the instruments. And I have an article on that entire history from 1990 to 2009, where we finally confirmed water. So that entire chronological order is there. If you're interested, you can check that out. So yeah, so that was water on the moon confirmed, sure shot. है, अच्छा खासा है, कोई डाउट नहीं है, अभी आगे क्या? Now the thing is, every every few times, like every now and then, every few years, people keep on saying, scientist का announcement आता है, NASA का आता है, ISRO का आता है, कि we found water on the moon, water on the moon, water on the moon. Now all of these are different types of water. So I just wanted to take a moment and a slide to clarify that. First is the recent one, the last week ka discovery jo tha, which is Sophia, NASA's airborne observatory, which I think is a great idea. So this is the airplane. It's a Boeing 747, and you can see an opening here. It's sort of a huge opening. The picture is small. Within that opening, there is a 3-meter infrared telescope, and the reason it is in the airplane is because if you try to use an infrared telescope and look up to the moon, observe the moon from the ground, the atmosphere of the earth is going to interfere. So it's on the plane instead, where you could go to a reasonable height where there is minimal interference, and then you could observe cosmic objects directly. So but it is still cheaper than sending an entire telescope in earth orbit, uh, just like the Hubble telescope, for instance. So it is sort of like a midway solution, and that's a great solution. I think this is the kind of uh, there are many such scientific endeavors being taken on by everyone across the globe, but this is something that people don't know about, and they just know about Hubble and big instruments. But these are the instruments which are actually contribute to a huge volume of science. So this telescope here, they observed the moon for some time, and what they detected was water molecules on the surface of the moon in the non-polar regions. So here they have shown where they found the water. So it's squarely in a non-polar region of the moon where there is lots of sunlight. So what is happening here? I just told you that on the moon there is lots of during daytime there's lots of sunlight. It's exposed to vacuum. It should just evaporate. So what's the deal here? So the deal here is this water is not free floating. It's not like the puddle that you have during monsoon on Earth. It is embedded inside minerals. Okay, and so so the moon's rocks, right? The surface rocks. This is a bright region again. So this bright region is rocky, and rocky areas mean there's lots of minerals, right? So that's just how rocks form. So the water is locked up inside. So remember when I said some of the water gets absorbed if there is enough time for that. So that absorbed water is locked inside the minerals on the moon, as is shown here in this illustration, right? So if you have water sandwiched between two minerals, then you are sort of safe. So this is the kind of capped water that they have found. Capped water is the right word here, that they have found on the moon last week, right? So this is different from the water which we found in the permanently shadowed regions. And before that, in 1999, in fact, uh, NASA spacecraft Cassini, which studied Saturn for 13 glorious years, it was launched in 1999, and it just went past the moon very quickly on its way to on its way to Saturn. And while passing by the moon, they were like, "Ki, let's do some practice of the instruments. I mean, we need to know कि अपना instrument काम करता है कि नहीं. Otherwise, when we reach Saturn and find out the instrument doesn't work, it's going to be a sad story." So they sort of turned on their instruments and did a practice run with the moon. And practice may they sort of hit a jackpot. So they had seen signs of this sort of capped water on the moon, which is represented here in this illustration. Again, this is an illustration, by the way. It's not a real picture. So they saw such trapped water molecules across the surface of the moon. Okay, but the reason the discovery was not announced then in 1999 is they were not sure if what they had found was water as in H2O or water in the form of hydroxyl groups, which is OH, right? So minerals tend to have lots of hydroxyl groups. So they were not sure. They could not differentiate if the smoking evidence, so what the spectrometer was catching was the line of hydroxyl or the water line. So they could not distinguish between the two, and therefore they did not claim that we have found water on the moon. It could just well be hydroxyl groups. So, but Sophia could distinguish between the two, and so finally we know that there is water on the moon, on the regular moon, and non-polar regions of the moon as well. So this is one thing. The second thing is coming to Chandrayaan 1. Now, what happened and what typically happens is, I've seen this thing as a science communicator, it really irritates me. It is whenever some big discovery happens, people will always find an Indian angle, even if there is not an Indian angle, right? And I think we should not do that. We should sort of stand on our own merits. So, what people started to claim is Chandrayaan 1 already found water on the moon. Just like this impact probe that LRO had, Chandrayaan 1 also had an impact probe, which was also directed to the polar regions on the moon. So the impact probe, which is called MIP here, which I'm pointing to, that probe went and crashed intentionally on the polar region, on the south pole of the moon. So, but it did not, there were no follow-up observations. Instead, this probe had a spectrometer on board. It had a mass spectrometer, to be specific, which basically sort of, you have a mass spectrometer, let's say you are flying a mass spectrometer on the way to crashing on the moon. So you are passing through the moon's thin atmosphere. So that air, as and when it passes through that spectrometer, you can detect what molecule is that. So that's essentially what a mass spectrometer does. And this chase instrument detected water molecules and water in the form of H2O on the in the atmosphere, thin atmosphere, exosphere of the moon. So yeah, so people started claiming this is H2O. We already detected that, but no, it is not relevant because the discovery by Sophia was on the non-polar regions and it was on the surface of the moon. This is in the exosphere of the moon, which is already a known fact that any water which ends up on the moon, a lot of it will end up evaporating and escaping. So you are bound to find some small amount anyway. I mean, it is a good discovery. I'm not discarding the discovery, but I'm saying that the discovery is very different from any of these discoveries, right? So yeah, this is a clarification of the types of water we have found on the moon. So one is the permanently shadowed regions, lots of water ice. Second is this sort of water on the surface of the moon, trapped inside minerals and rocks on the moon. And the third is on in the atmosphere of the moon. So I hope that every one of you is clear on these things. The second thing I want to clarify is the amount that there is on the moon. So this trapped water is very little. If you try to estimate, and they sort of tried an estimate based on Sophia results, this is so less that it's drier than the driest deserts on Earth. Sahara has more water than the moon has in the non-polar regions. So if you're thinking about, digging up that water, no luck. It's just not going to work. So yeah, so coming back again to the permanently shadowed regions and tying it to the core problem. Why aren't we living on the moon already? Right? So,
Jatan, just to tell you, we're at about 50 minutes right now.
hmm,
Yeah. So you have about 10, 15 minutes.
okay, great. So how much water does the moon have? And specifically in these dark regions. Okay. So the estimate is from the radar observations by Chandrayaan 1 and the radar on board LRO, they estimated 600 billion kg of water ice. Okay, and how much is that anyway? So Arnab sir here did some calculations, and according to his calculations, he found that if you, let's say, take an Olympic swimming pool and you calculate its volume, which is length into breadth into depth, then you would get about 2,500 liters of water, right? And that is equivalent. If you divide 600 billion kg by 2,500, you would get about 240,000 Olympic swimming pools that you can fill with the water that is present in the permanently shadowed regions of the moon. Okay, and just to be clear, this estimate is from the Chandrayaan 1 and LRO radar observations. Now, how much is this?
Just a correction. It's 2,500 meter cube. 2,500 meter
Yes.
cube. So it's 2.5 million liters. Olympic swimming pool is like 2.5 million liters.
Is it million liters?
Yeah, 2.5.
Okay.
No, not like one Olympic swimming pool is 2.5 million liters or 2,500 meter cube. The just multiply 15 to 2,500 2. The
Yeah,
links are
yeah.
in meters. And so the
So
amount of water,
it's
on the
2.5.
moon, yeah, the amount of water in the moon is about 240,000 pools worth of water.
Right, right. So it's
Yeah,
2.5 megaliter, right? The
megaliters.
Olympic
Yeah,
swimming pool. Yeah,
yeah,
yeah. Okay.
megaliters.
Yeah, yeah. Okay.
It's megaliters.
Okay. Okay. So basically, the water on the moon is in the permanently shadowed regions is you can fill up 240,000 Olympic swimming pools with that. But how much is that anyway? So if you look at Mumbai's daily water consumption, it is 150 times less. But this is the daily consumption. All right. So essentially, you would end up consuming that water in 150 days, right? And this is also to put it into perspective with the Koina Dam, which is one of the largest dams in Maharashtra, that has 4.7 times more water than the 600 billion kg present on the moon, right? So the Koina Dam has more water, almost 5 times than the moon water. And the Lake Superior, which is the largest freshwater lake in the world, it is in America, it has 20,000 times more water. So just to give you that context, but the important thing to remember here is that the 600 billion kg here is a lower estimate. It's a lower amount. So you know that there is minimum this much, but we don't know how much more there is. And the reason we don't know how much more there is that it depends on the limit of the radar. So Chandrayaan 1 radar and the LRO radar could not penetrate the beyond 1.5 meters on the moon. So if the water ice is present like a iceberg, like a glacier, let's say, like if this ice present all the way down to 2 meters, 3 meters, 5 meters, then we don't know, right? So which is why the Chandrayaan 2 orbiter has an upgraded radar which can have a better depth sensing, so it can go up to 3 meters approximately. And so you can actually get to know if the water ice is present to what depths. So based on the depth, you will be able to get a much better estimate from the Chandrayaan 2 orbiter once its results are out. So everyone was focusing on the Chandrayaan 2 lander, but everyone forgot about nobody knew about the Chandrayaan 2 orbiter. In fact, ISRO themselves did not care about mentioning this fact that the Chandrayaan 2 orbiter is going to quantify exactly how much water do we have. And so now coming to the last part of my session, uh, and tying all of what we discussed together. So we already discussed that the area on the lunar poles are rocky. You have large craters. It's very difficult to land there safely. But so that's the one part. So which is why nobody has attempted to send a lander there. The second part is, as we discussed, there's very little sunlight. Okay, and the any small rock that comes in your way will block. So even if you somehow manage to land in this on this crater rim, let's say, right? Because these are large craters, these are 100-kilometer wide craters. So this crater rim is like fairly huge. You have good enough area to land on the crater rim. So let's say if you land in one of those crater rims, right? Even then, if there are small obstacles there, and there are small obstacles there, in fact, you can see some craters here as well, right? It's still a rocky area. So if you have any obstacle there, you will end up losing light again. So what you are seeing here on the screen right now is a yearly map of the sunlight on the moon's pole, on the south pole of the moon specifically, where what you do essentially, you know how you take exposure in your camera? You just leave the camera on for you don't allow the shutter to close for 5 seconds, 10 seconds, and so on. So a similar kind of experiment the NASA LRO did on the south pole of the moon. It just kept on observing the south pole as and when it could, for an entire year and more. So if you stack that exposure one over the other, you would see that there are only very few areas which are having near continuous sunlight for an entire year, which are these bright pixels. And the other areas in the entire year, you're just not getting any sunlight, right? So your job is to land here in this small white area is what you have to nail the landing on, right? Now, looking at the terrain, I already said it's rocky and it's bad, but just how bad it is. So on the left, you have the slope, sorry, the height, and on the right, you have the slope, right? So the height here, if you cannot read the screen, it is 2 kilometers high, as high as 2 kilometers from the surface, which would be the rims and the mountains and the elevated areas. So you can see this, the rim of the crater is higher than the local surface, and the depth is inside the craters, it's as low as 3 kilometers. So you are looking at a 3 kilometer abyss here essentially. So, and if you look at the slope, it is a much worse story, right? It's not just the height, it's the slope. The slope, if you're on the rim of the Shackleton crater, then if you on the right of you, if you're here on your right, you have slopes much worse than 30 degrees, right? So let's say you landed, if you land on the rim, it's somewhat rocky, and you try to land a lander, okay, you somehow manage that great engineering feat. But if you miss by 100 meters or so in the rocky areas, you can see that even here, so this is purple color, right? The purple corresponds to 15-20 degrees. So no matter where you land, you still have very bad slopes. So essentially, you are looking at a realistic scenario of landing like this, or like this, or like that. And the moment you pop out your rover, the rover is just going to slide down and into the darkness, forever lost, right? So, and of course, as I said, the sun is very close to the horizon. So if you have a slope like this and the sun is here, you lose the sun. If you have a slope like this, the sun is here, you lose the sun. So keeping track of the sun is very difficult, and you can see that here. So you have bad terrain, you have bad sunlight, you have bad slopes, and to make matters worse, apart from losing your rover, you have bad communication. So even earth is visible only half the time from the polar regions of the moon. So since you are only getting earth visibility about half the time and half the time you're not, if you have some issue with the rover or the lander cannot communicate back to earth, and so you cannot know if there's something wrong for an entire 7 days, for example, right? Or sorry, for 14 days. So a lunar day is 28 days. So you would have earth communication for 14 days at best, and then you would not have earth communication for 14 days approximately. So the rover which you build to land there and collect water for you if you are to live there, then that rover will not be able to communicate for 14 days if something is wrong. In fact, it would not even know where it is properly if it goes into a region where it cannot navigate. So this is the crux of the issue, that you have bad sunlight, you have bad slope, bad terrain, bad communication, and you have bad temperatures, right? So we already discussed nighttime temperatures are minus 180 degrees Celsius, but these are areas which are never getting sunlight at all for 4 billion years. So these areas are as cold as minus 250 degrees Celsius in some cases, and on an average, they are as cold as minus 220 degrees Celsius. So this is colder than Pluto. Now, Pluto is so far away, it gets 1,500 times less light on average than the permanently shadowed region on the moon. So despite being 1500, despite getting 1500 times less light, Pluto is still relatively hotter than the coldest region in the PSR on the moon. So your rover not just has to navigate that wonky terrain, it has to survive minus 240 degrees Celsius. There are not, the batteries are not available with the technology right now, and correct me if I'm wrong here, Arnav, but current technology doesn't allow for batteries which work in such cold environments. So basically you would end up having a requirement for a power source which can keep your batteries warm and the electronics warm, right, on top of all the issues present otherwise. So you basically, you want to find an area on the moon which has a good source, flattish area where you can land. You need solar illumination, you need earth communication, you need a relatively mild terrain like 30-degree slopes. Nahi, you want something like 15-degree slopes, and you want permanently shadowed regions which are small in size, not these giant 100-kilometer abyss ones. You want something which are, small craters that you can sort of navigate and get out of if there's some trouble, right? So you want all of these things together. So this small area here is what your Goldilocks site looks like. And finding that site is exactly what the Chandrayaan 2 orbiter and the NASA LRO have been doing since so many years. So they have been trying to gather all the data of how much water there is exactly, should we even bother going, and where do you find a good Goldilocks site that has all of these features, right? And they found, so far, they found these promising sites on the rims of these craters, which I've highlighted in blue. And these sites have nearby smaller regions. So you can see small, small craters where my mouse cursor is, right? So there are many, many small permanently shadowed regions, which will also have water ice, which you can go and tap into. So they have identified such sites, but of course you need more data and you need to wait for the results from Chandrayaan 2 orbiter to come in to have a good estimate on how much water there really is. And then you sort of, land somewhere here, and you can traverse your way by, going around sites which have light. So these white pixels are the areas which have light, and you should not have bad slopes. So with all of these data overlaid, you can easily find a good way to landing in a gentleish area and then finding your way. Now the good news is that I just told you, and I'm nearing the end of my slide, I just told you all the reasons why we haven't done it and what we are doing to remedy that. The good news is NASA is sending a lander mission to do exactly that. In 2023, that's the current target date. It's called Viper. It will be a lander. The lander is not visible in this picture. And there will be a rover which will somewhat look like this. There will be a drill at the bottom of the rover, which is not visible in the picture. And it will sort of do exactly this. It will land somewhere. As of now, it's not been finalized yet, but it will land somewhere uh, in these elevated areas where there's sunlight, and it can reach a permanently shadowed region within 2-3 kilometers range, and then travel its way to the PSR, and then sort of go inside the PSR, use its spectrometer to understand where the water is, map it, and so on, and then use its drill to drill 1.5 to 2 meters inside the permanently shadowed region, mind you, in minus 220 degrees Celsius, with no sunlight, no earth communication, fully autonomous for days. And then it will sort of come back out by retracing its path. To enable it to do that, it will have a host of sensors like, a lidar, for example, which will work in the dark. So a laser based sensor, so which will allow it to map the area. By the way, the iPhone 12, which was announced earlier this month, the iPhone 12 Pros also have lidar. So if this is your iPhone, the flash that you see here, the flash size, that's the size of the lidar that the iPhone has. And that iPhone can sort of scan a room in 1 or 2 seconds. So of course, this thing will have a super advanced lidar. There is no cost concern here compared to the iPhone. So it will have a lidar to see in the dark. And the idea is to basically demonstrate that there is enough water physically present there that you can dig up, and demonstrate that okay, now it is viable enough for humans to go on the moon and think about placing habitats. So only after this mission or any such similar mission happens can you actually think about sending NASA Artemis humans on the moon, or China humans on the moon, or anything else, right? So yeah, that brings us to the end of the session. I hope I have highlighted the core problem with uh, why haven't we why haven't we had a human settlement on the moon already, how much water there actually is on the moon, and what are the differences in the water that they keep on finding on the moon. So just to end my session with, you can find more on the moon on my blog. So I'll just very quickly demonstrate that. and I will end the session. So just give me 1 sec. Yeah. So I have a dedicated moon page. I am a full-blown lunatic. So on the very first, so you just go to jatan.space and you will find all my articles across all categories. And there is the moon category on which I have stories on the moon. So you can read the latest ones or the curated moon page where I have stories by Apollo, Chandrayaan, interview with the mission director of Chandrayaan 1, and stories on moon science and moon exploration and so on. So I would encourage you to go and explore and know more about the moon and give me feedback on what you liked, what you did not like.
Okay,
And
but hopefully you'll take some questions now as well, right?
yes, I'll do that.
Okay, so there's a lot of questions on the chat channel.
Okay.
Really lots of questions. So let me just start at the very beginning, and we'll take the ones which are related to the moon first. And questions like, okay, so let's see, let's take. So what was the trigger that initiated this? The bombardment of. Do people know why there was a sudden bombardment of
Yes. So basically,
meteorites with water for many billion years ago in the evolution of the solar system?
yes. So basically, what had happened was, one second. Yeah. So basically, what had happened was we know that for some reason, Jupiter and Saturn and the other two giant planets, Uranus and Neptune, uh, they did not form where they are currently. They formed somewhere on the inside and then migrated outwards. This happens. We have seen this sort of the signs of this happening in other solar systems, in other star systems, where we see gravitational effects playing out. So essentially, what happened is Jupiter and Saturn and the other two gas giants, ice giants, they migrated from inward to outward in the solar system, and in that process, because they have this huge gravity, they sort of lofted the asteroids and the comets, whichever came in their way, and that's the reason why this rampant distribution of asteroids and comets happened in the first place. So all of these craters on the moon are essentially a result of that rampant process.
Okay. Um, you started off talking about rockets, saying that we don't have anything like the Saturn V now. But is there an advantage to the fact that we have reusable rockets? The fact that the Falcon type of stuff is actually reusable. So, well, even if you can take only a lesser payload per trip, you can maybe, it's overall it's still not an impossible task to go with smaller reusable rockets.
Right. So the thing is, in the case of rockets, to answer this particular question in brief, reusable rockets are not that useful in this context. To expand upon it, the reason why they're not that useful is once you start a reuse, the capacity I mentioned for the Falcon Heavy was to the moon. It can do 8,000 kgs. By that I meant it could do 8,000 kgs if you use all of these boosters and not reuse them. If you reuse them, your capacity goes even down, because to reuse you need to have some fuel left which you can use to come back and land, right? So if you reuse, the capacity is somewhere around 5,000 kgs, and essentially your capacity goes so low that you would need so many flights to go to the moon, and you need all of those flights to be successful. If one of them goes down, then you are at a higher risk because you only got half the stuff there. What happens if you transport two astronauts but you're not able to transport the material required for them in the next flight? So in the case of the moon, you need substantial amounts of payload capacity as a bare minimum, like at least 20,000 kilo to chahiye, and after that you can start thinking about reusable stuff.
Okay, great. I hope that takes care of your question, Ram. Okay, the next one is the water in the moon in a liquid or solid form? I think you've answered that. It is water ice, or trapped water between in minerals.
It's water ice in the case of PSR. In the case of mineral, if it is sandwiched between the two mineral layers, and if there is enough pressure there, then it could be in the form of liquid water. But it's not on the surface that it's liquid water.
Okay. Another sort of interesting question is: are there legal or social barriers which are even more challenging than the technical ones? who owns the water on the moon? What if you contaminate the water on the moon? Is it ethical to go and do that? Questions like this.
That's a great question. So, and the thing is, there's no clear answer to that yet. So there's something called the Outer Moon Treaty and the Outer Space Treaty, and those sort of deal with these questions where they say that properties outside Earth in space belong to everyone, and they can essentially the resource is to be shared by everyone and anyone. But the thing is, as of now, there is no body to enforce that. And the countries who sign these treaties, some countries have signed the Outer Space Treaty but have not signed the Moon Treaty in specific, and some have not signed the Outer Space one but have signed the Moon one, and so on. So there is discrepancy in that, and there's no shared consensus among the major countries of the world who have or are going to build these capabilities. So as of yet, it's sort of like open ground and open territory with no regulatory body to take care of these things, just like we have for Earth orbit. Earth orbit also, we have some regulatory bodies to say, okay, you cannot have so many satellites in this orbit. You need to tell me, okay, what your orbit will be so that it doesn't interfere with the other. So there is some regulation in Earth orbit, but there's not enough regulation or nearly no regulation for the moon as of yet.
Okay. A question which has come a couple of times is, can life exist or grow slowly on the moon?
As far as we know, no, because there is no complex chemistry happening there, and there is no sign of complex chemistry of any form, carbon or otherwise. So, and the temperatures and pressures are just too bad and too harsh. So, I would say no.
Okay. And the water in the non-polar regions, are they in craters or are they not in craters?
They are also inside craters, but here the difference is the craters are large, many of these, and since they are in non-polar regions, the sun is high up in the sky, right? Because you are towards the equator, so the sun can go high up in the sky depending on your latitude. So you have plenty of sunlight beaming in. So there's no difference between a crater and a non-crater on the non-polar regions per se. So it is both inside the crater and outside.
Okay. And uh, what is it? Let's see. Uh, does the amount of water on the moon depend on the low gravity of the moon?
It does, actually. That's a great question. So the gravity is a major factor in how much water can you retain after you have got it. So when I said asteroids and comets bombarded both the moon and the earth in the early times of the solar system, the reason earth could retain so much water is because of its gravity, right? So even if, let's say, the comet comes, strikes the earth, the water evaporates, but even after evaporating, it will still stay in the atmosphere. And once things have cooled down, it can condense and come back, right? But for the moon, because of its low gravity, there's just not enough gravity to, retain so much atmosphere and therefore have that water come back which you lost.
Okay. And another question is, uh, only depending on water,
Hmm.
without having an atmosphere, because it's related, is it good to be colonizing the moon?
Only depending on water, as in?
I mean, would it be preferential to try to put humans in a place which had an atmosphere apart and other and also water? I mean,
Okay, yeah.
I guess
So,
it
so the issue
no
with
other place has an oxygen atmosphere anyway, so it doesn't matter,
yeah,
right?
yeah, right. So see, water is there on Mars as well, but there's no oxygen atmosphere. So anyway, we'll have to do a lot of work to do that. But the main advantage of the moon is, regardless of how much water it turns out to be, after all, the main advantage is its proximity, right? And the everything else, including Mars, is just so far away that there's no question of going there. The amount of energy you would spend to go there will be far more than you would spend to dig up that water on the moon. So that's one thing. The second thing is, uh, even taking that water out of Earth's gravity, and let's say we send water on the moon for astronauts living there. As I said, this one water bottle costs $1 million per kg. But once you have a method set up on the moon where you can extract that water in an industrial fashion, once you do that investment, it will be far, far, far cheaper to keep on doing that rather than taking this little amounts of water and expending that insane amounts of costs to keep on sending rockets. So that's the idea behind these pushing for these discoveries in the first place.
Okay, so let's see. Um, could we use space mirrors to redirect sunlight into the craters?
Yeah, I mean in principle, but the problem is uh, space mirrors would be large and heavy, and the best mirrors we have on Earth, which are smooth and flat and nice, are super heavy and they face strong engineering challenges. They need a good base and everything. So you could do that in principle, but you would face other challenges like in orbit in around the moon, where the space mirror would be. The To keep it in orbit would be a challenge because the moon is not an ideal sphere, unlike what physicists would like to believe. So the moon is not an ideal sphere, and therefore there are gravity gradients. So some areas will have higher gravity, lower. So your mirror will keep on shifting orbit. So you would need some mechanism to keep that mirror in place and so on, or keep on doing its job. So it will be much far more energy expenditure to be doing that than to just go there and do something else with it.
Okay, and can you tell us a bit more about the Chandrayaan 2 lander? And I mean, the Chandrayaan 2 mission, people think it failed, but actually, it's still doing a lot of good stuff. And
Right.
it's
So
the
there's
it's
two
the
parts to it.
rover which probably was the only
Right.
real failure.
So there's two parts to it. First part is the lander, which also had the rover, and both the lander and the rover failed, as in the lander crashed on the surface of the moon. So that part of the mission failed. And that was again not in the two polar regions. The orbiter is still functioning. It was put into orbit before the lander attempted the landing. So the orbiter is still functioning, and it is expected to function for at least 6 more years, at least assuming there's no other issues cropping up. But so far, it looks to be functioning great, and we are expecting data from it to come very soon. So the orbiter is still doing the job. The lander and rover part of it failed.
Okay. If one, I mean, I guess these are sort of more hypothetical questions. If we do send astronauts to the moon in the future, is it better to make it a one-way trip to allow more scientific equipment to be sent there instead of sending fuel needed for people to come back from there?
Um, I mean, if you are able to guarantee those astronauts to be safe and alive there, then sure, you could send them on a one-way trip. But I don't see an organizational paradigm in which this sort of a setting would be accepted by anyone.
Okay. And let's see.
So just to add one quick thing, even if you are able to guarantee that okay, those astronauts will be taken care of by these mechanisms there, in any event, there's no guarantee of that working because there's always an error margin that you have to keep in mind. So even in that edge case, you always need to account for a trajectory back, and that's how all human missions to anywhere in space are built. So that's never going to happen.
Okay. Is there water likely in asteroids as well? And can we actually sort of remote sense near Earth asteroids to see if it's possible to get water there?
Yes, it is there, and that's exactly how we found water in the near Earth asteroids and the comets which have trajectories which pass close to Earth. So we have found water on asteroids, both near Earth ones and the ones in the main asteroid belt, and in comets which pass close to Earth by using spectrometers on spacecraft and which go near to those asteroids, or from radar-based observations of near Earth asteroids. So yes, there is water on those objects, and we know that it is there, and we know it is in large amounts. But the problem is even the near earth asteroids are relatively farther away than the moon is. So sort of, if you develop technologies, and those who have more or less similar engineering challenges like the terrain and the temperature and all the things which I talked about, the moon is very similarly applied on the asteroids and the comets, with some differences based on their geology, based on their proper physical properties. So the idea is that if you are able to demonstrate this engineering, if you are able to solve this engineering problem on the moon, then you are able to solve it anywhere in the solar system. So that's why the focus is on the moon.
Okay. Uh, why does I mean, this is not related to water, but why does the moon have so many craters but the Earth doesn't?
That's a very good question. So the moon doesn't have water because moon doesn't have craters because it
The moon
doesn't have
has
an atmosphere.
the
Sorry, the
moon
moon
has
has
craters. The moon has craters.
sorry. The moon has craters because it doesn't have an atmosphere or running liquids on its surface, right? So, for example, if you see the dark regions of the moon, you would not see many craters there in the dark regions because that was lava flow, which has now solidified. So, which sort of any craters which were there have been, uh, they have essentially been drowned inside the lava, and now the lava has solidified. But the moon doesn't even have an atmosphere, so there's no weathering effects, right? So on Earth, you have wind weathering effects, and you have things like running water, which sort of clears away any landmarks or footprints or any such marks of craters on the surface. So because of the active geological nature of Earth, the Earth doesn't preserve those craters very well. So we have very few craters which are visible, and everything else has been washed away or cleared away by the air over time, erosion over time. But on the moon, there's no such process. So we see all of that intact more or less, and which is why
Okay.
we need to go to the moon to learn more about the past.
Okay. And okay, let's take one final question before we end. There are probably a lot more. You can take a look at the chat as well sometime. Um, uh, let's see, is there an interesting one which we should look at? And why don't we get bombarded by asteroids and comets as much these days as we did 4 billion years ago? Because I think he explained it because that was when Jupiter and Saturn and the big planets
Yeah,
were moving
yeah,
around. Now our solar system is like nice and old and stable, and
yeah.
we really don't have too many loose cannons,
Yes,
asteroids
yes, yes,
around.
yes. That's it.
Yeah. Okay. Here's one. How much of this data that is coming out of all these spacecraft, I'm sort of interpreting this question, is actually, you know, before it comes out in the public domain, are we releasing, are all NASA, ISRO, do they release this data all as they come out of the sensors in the public domain, or is it coming out only after a while?
No, so it comes out after a while depending on the agency. So NASA has rules per mission. Typically, the average rule for NASA is that after a mission has sent data of whatever, the data should be available for the public in a good organized format 1 year after the data has been sent back by the mission. That's the average rate. And for some missions, they make exceptions. So for LRO, for example, since it is a critical orbital for many things, sometimes they release data just within 2 months after being beamed back. In the case of ISRO, they typically do a year after the mission has sent the data. But in practice, in real life, unko bahut time lag jata hai, and that's one of the concerns with ISRO. The Chandrayaan 2 data already it's been more than a year. It's not come back yet. None of it. Sorry, it's not been released yet. I mean, so.
Okay. And with that, I think we should sort of say a big thank you to Jatan. Thanks a lot for.
Arnab, there is a question on the Facebook.
Okay, yes, go ahead. Go ahead. You were supposed to tell me. Go ahead. Please go ahead.
Yeah. Jatan, is there any discovery of heavy minerals on the moon which can be used by mankind on Earth for energy needs or otherwise?
Yes, not in terms of energy. So that's a good question, and I should use this space to clarify the helium-3 thing, which keeps on popping up in the media again and again. There is no clear sign of substantial amounts of helium-3 on the moon. So in terms of using that as an energy source, so far there is absolutely no evidence of being able to do that. But we have found metals for not for energy sources, but we have found metals like titanium and aluminum on the moon scattered across the moon. So those are industrial metals which will be useful in setting up habitats and industries on the moon in the future. So that is there, but the power source primarily still needs to come from either solar or from this water that you are extracting in some way or the other.
Okay, any other questions on Facebook?
No, that's all.
Okay, so yeah, in which case I would just like to end by sharing the Jatan, can I share my screen?
Yeah, I'll stop it. Yes.
I will just share the announcements of the next few Chandrayaan Ys. just to tell you that this month we're going to have a Chai and Why on every Sunday of the month. And the next 4 Chai and Whys this month are going to be on the Nobel Prize, starting November 8th with the Physiology Medicine Prize on Hepatitis C. 15th, we're going to have the first part of the Physics Prize on relativity and black holes, followed by 22nd on CRISPR, the Chemistry Prize, and we'll end again with the black hole at the center of the Milky Way. So join us every Sunday at 11 o'clock for Chai and Why this November. Thank you for watching, and stay safe. Pandemic's still going on; it's not over, and we'll see you there at Chai and Why. Till that time, thanks a lot.